Negative feedback helps to maintain homeostasis. Our systems are always receiving feedback at any given time. We're getting this information that is coming back to the control center to tell the control center what is happening around it in the environment around it, or in the environment of our body. It's not necessarily right there around the control center. And this idea of negative feedback can sometimes be a little confusing to students. So I want to go through this carefully. You might get it, and maybe you understand it, and you don't need this extra explanation. And so feel free to move on if that's really your case. And that's true with any of these videos. If you get to a point where you're like, okay, I get this, shut up already, you can fast forward the videos, you can turn them off, you can just move on with your life. So that's the nice thing about these things. But the goal of negative feedback is to essentially turn off the air conditioner or turn off the response that is being generated. And so the key here is that it opposes or negates the original stimuli. Okay? And it's absolutely critical and necessary. Without negative feedback, we end up with a runaway train. And we'll talk about that type of situation a little bit later. Now we're going to move on and look at this example, but actually what I want to do, and I'll let you study this and look at this on your own, I want to walk you through it again in my own place. And in fact, instead of using this screen here, let's go ahead and open up a new board so that we have unlimited space here. So remember that we talked about, I'm going to draw a single cell, and this time I'm going to put it in the middle here. And so here's my nucleus, and we talked about there being receptors in the center of this cell, or in the membrane of this cell. And I'm going to stick with temperature because that's what we've been using, and so that's probably going to be the easiest that we understand. And some of this, by the way, is, I know I've talked about it in context previously, but let's look at this. And what we should see here, okay, is that we're going to get some type of stimuli. And let's assume, for our purposes, that the original stimuli, what's a good color for heat? We're going to say orange. The original stimuli is thermal energy. And so this thermal energy, okay, this little line is going to represent my energy. This is my thermal energy. Okay. And maybe I've done this before. I feel like I've talked about this in a video before, but we'll just repeat this because it's important to understand. This thermal energy is going to activate this receptor. And in response, this is going to generate information inside the cell. And if that cell happens to be in, let's say, the hypothalamus, which is an important homeostatic region of the brain. Okay, let's say that that's where this cell is located. It's in the hypothalamus. In response to it, let's turn this into a neuron because it should be a neuron. Okay. And so we're going to turn this baby into a neuron, and I'm going to draw a axon here, kind of a funny looking axon, but we're going to draw this axon here. And we're going to assume that the output signal that is generated is an electrical signal. So I'm going to put this electric green to represent this electrical signal that is going to be generated from the cell and travel down the axon to another neuron, which will then generate another electrical signal. Now, this is going to allow the information, so let's label this. We're going to call this thermal energy the stimuli. We're going to call this little receptor dude here, this little guy right here, this is going to be my receptor or my sensor. We could also call the whole cell a sensor, and that's sometimes done as well. We could call, in fact, if this were a sensory neuron in the sensory nervous system, we would call the entire cell the sensor. Okay, so that's fine. But the region, the hypothalamus, would then be the control center. So I'm going to just call the receptor my sensor, and I'm going to put a little bracket here, and I'm going to call my neural network, my control center, okay, or my integrating center. And as we send this signal out, we'll activate other neurons, and that electrical activity becomes the output signal. So let me go ahead and say we're going to activate this neuron here, just because I want to kind of illustrate the fact that we can send signals in different directions. And those will each receive an electrical signal. So here we go. I'm oversimplifying it. You're going to learn more about how neurons work. And so this activation of other neurons through the electrical signal, that's my output signal. Okay. Now, eventually that signal, and I'm not going to draw all the details here, but that signal is going to reach two places. Okay. So we're going to reach the first place is going to be, what do I want to draw? I guess we'll do purple. These glands, and I'm going to draw it, going to look kind of like this, and it's going to be embedded in the skin. So let's draw some skin cells in here. Okay, here's my stratified squamous epithelium, keratinized. And what are we going to do? We're going to release this salty substance onto our skin, and so we're going to sweat. And so my sweat is going to come out onto my skin, and so consequently what that's going to do is get my skin wet, and the water molecules will leave. So water molecule is going to evaporate into the atmosphere and become gas. Okay. And in that process, that's going to absorb some energy. That's going to require some energy. And so we're getting what we call evaporative cooling here. And so that would be through the nervous system, the output signal through the nervous system. And so this is an important process that we have going on. But then there's another process that you need to know about. And that would be if we look at the blood vessels, so let's go ahead and draw kind of a blood vessel here. And we have that blood vessel. If this is an arterial, it's going to have some smooth muscle cells around it. Sad that my cells, whether they're smooth muscle cells or whether they're simple squamous epithelium, they all kind of look the same. Art class is not part of my skill set. So in response to this, these blood vessels will open up, and what that does is it's actually going to bring, that doesn't look like it's opening up, sorry. It's going to dilate, it's going to enlarge and stretch out a little bit, and that's going to increase the blood flow. Well, if we're increasing the blood flow in the region right below the epidermis, okay, we are going to get heat exchange. Let's go back to my orange color here. So we're going to get the exchange of thermal energy, and it's going to exchange with the water that's on the surface, and that's going to increase the evaporative cooling. All of this has the effect of cooling down the blood. Heat from the core body is taken to the surface of the skin by the blood, and the water that is evaporating away removes heat from that blood, not because of the direct contact, but because the blood is right below the surface of the skin. And we become, when we're hot, we get flushed, and that's because of the increased blood flow to our skin. Our cheeks get rosy, we look hot, we look flushed. And so once this has continued for a while, what that actually does is removes the initial stimuli. Once that stimuli is gone, this entire process stops working. And we call that whole thing, so the removal of the stimuli, as the cooling process, cooling things down, eliminates that thermal energy that was tripping the sensor. That's the process that is called negative feedback. And we can get negative feedback. It can look like a number of different things. Most often, it is the removal of the original stimuli. Let me correct myself. I probably shouldn't say most often because I don't know that for sure. How about I just say often instead? I'm going to erase my little control center just so I can write it down. And I'm going to put down here, sometimes it's the product. Okay, it's the product of the effector. A great example of this is in the endocrine system. Let's say our metabolism is running a little cold. We need a little bit more energy. And so that's gonna be my stimuli is reduced energy. And in order to bring us back to homeostasis, okay, that reduced energy is going to trigger the production of a hormone called thyroid hormone. Okay? We'll get into this in more detail, so don't freak out. Thyroid hormone. But that thyroid hormone then becomes the product that stops the production of thyroid hormone. And that might seem counterintuitive until you go back to your set point. If my set point for thyroid hormone is here, and my values are too low, not enough energy, okay? Not enough energy. Start making more thyroid hormone, my energy levels are going to go up. Keep making thyroid hormone, and my energy levels are going to continue to go up. It might sound like a great thing to have more energy, but it actually can quickly become nervous energy, fast heart rate, things are out of control, and that's not a pleasant feeling. So we want to be able to bring this right back down. So how do we do that? We do that by preventing the production of more thyroid hormone. Meanwhile, your liver is saying, let's get rid of this. And so it's a lot like my analogy of the leaky house, where the liver is essentially breaking down thyroid hormone, and when the thyroid hormone is broken down, we go back down, and when it's too low, we go back up, and so we get this oscillation that is very similar to the oscillation in temperature that we get. And so in this case, rather than the negative feedback being removal of the original stimuli, it's actually the product made by the effector organ or tissue. And we'll get a chance to really look into this, but you guys got to dig into this. This is super important to understand what negative feedback is and what it's not. With that in mind, let's go back here and talk about the runaway train effect. And for the runaway train effect, we actually call that positive feedback. Instead of opposing the original stimuli, this amplifies the signal and continues to amplify the signal. And so we do, in effect, get a runaway train where the train goes faster and faster and faster and faster and faster. Runaway trains are not about restoring homeostasis, just the opposite. The faster the train moves, the more homeostasis is lost. If these positive feedback processes were allowed to continue indefinitely, they would most absolutely lead to a pathology and perhaps even death. It would be a serious problem. We do have positive feedback mechanisms that occur naturally, and these are usually short-lived, relatively speaking, and they serve a purpose. One of the best examples of this, of a positive feedback process, or we call it a feedback loop, okay, would be childbirth. As the baby's head pushes against the cervix, it's going to cause that cervix to stretch out. And that actually activates sensory receptors in that cervix. And that generates a signal that is sent to the brain. You'll find this a lot. The brain is very often the control center. And in response to that stimuli, the brain will release or stimulate the pituitary gland to release a chemical called oxytocin. Oxytocin travels through the bloodstream to the uterus, where it causes the uterus to contract. And as the uterus contracts, the baby's head pushes against the cervix even more, which causes the cervix to stretch even more, and that generates even more of a signal back to the brain, and that's going to cause more release of oxytocin, which causes more contractions, and the process continues on and on and on. And what actually stops it? What stops this runaway train, which is called parturition or labor? And the answer is that the child or the fetus is born. It exits the birth canal, and that is the process that stops it, because once the fetus has exited the body, then that head of the fetus is not stretching, is not pushing against the cervix. Now, you actually do get a continuation of this process when you're birthing the afterbirth or the placenta as well. But in general, simple terms, that's the basic idea. The absence of the original stimuli is what stops this from happening. And childbirth will continue until the stimuli, the source of the stimuli, the baby's head pushing against the cervix, is gone. Now, if that were to continue indefinitely, labor is hard work. It's painful, it's difficult, it's hard on the mother, and eventually, if it continues for too long, exhaustion ensues, and that can lead to the death of the mother if the fetus does not actually get born, which of course is why modern day science, modern day medicine allows methods for interfering in this. If the baby's just not going to come, that's when you might do a C-section to remove the baby, and that, or maybe the doctor will decide that a vaginal birth is not likely to succeed and will just do a preemptive, I guess. I don't even think that's the correct medical term, but the basic idea, preemptive surgery. There are other examples of positive feedback that occur in the body. Blood clotting is one of them. The clotting process is a positive feedback process where the chemicals from the broken skin, or broken tissue, will be, and it's actually collagen. We'll look at this in more detail when we talk about blood clotting or hemostasis. Not to be confused with homeostasis. Yet they're related. They're not the exact same word, but they are related to each other. And the chemicals will trigger the activation of molecules, or not molecules, cell products called platelets. And then those platelets release even more chemicals, which will stimulate the activation of even more platelets. And so consequently, the blood clot enlarges significantly as platelets activate more platelets, which activate more platelets, which activate more platelets. We also have clotting factors where a similar process works as well. Now, how does this all end? There are going to be molecules secreted from healthy cells, and we will get a chance to talk about this in more detail, that essentially put an end to this process once the bleeding has stopped. So just like in the previous example, once the baby was born, the positive feedback process ended, I should say. And the same thing here is once we've reached an end of the bleeding, once it stops, then that positive feedback process also stops. We're going to see positive feedback processes in the action potential of the neuron. We're going to see it some with the immune system. We'll encounter various examples, but understand that positive feedback is always short-lived. If it were not, we would very quickly end up with a pathology and death. You can imagine the danger and harm that a blood clot that just continued to form, that just got bigger and bigger and bigger, would cause. If it were to break free, for example, and head to the brain or the lungs or the heart, that would cause a serious problem, possibly death. And so it's obviously not a desired effect to have this positive feedback continue indefinitely.